Weekly Robot News. Hello viewers, welcome back to your one-stop shop for all news robotics. We're back once more with the latest, sometimes shocking, happenings of the robotic tech world. From robot dentists sending autonomous vehicles off-roading, pigeon-scaring drones, to legged and insect-sized robots. So without further ado, let's jump right into our weekly updates. However, before we do, we request you to subscribe to our channel and press the bell icon to never miss another upload of ours. Having said that, let's get right into it. Highlights of the week. The oral sampling robot. Until we come up with something less unpleasant, all of the most reliable ways of determining whether you're playing host to even the tiniest little bit of COVID-19 that we have right now involve some flavor of jamming a sampling device into a mucousy orifice that doesn't appreciate having sampling devices jammed into it. Whether it's farther up your nose than you thought possible, or down your throat to the point at which you involuntarily attempt to punch the nurse in the face, I'm very sorry about that. Taking samples of disgusting goo is no fun for patients, and probably even less fun for medical professionals, especially when there's a reasonable chance that the mucus you're now elbow deep in is aversing with COVID. The process of taking orophageal swab sampling is dull, dirty, and dangerous all at once, making it an ideal task for a robot to do instead, as long as that robot can avoid violently stabbing you in the throat. In a paper published in IEEE Robotics and Automation Letters, researchers from the Shenzhen Institute of Artificial Intelligence and Robotics for Society introduced the robot in the video above, designed to protect the safety of medical staff during the sampling process, as well as free them up to do more useful and less gross things. Since, let's face it, taking these samples is not fun for anyone. DARPA's RACER program sends high-speed autonomous vehicles off-road. DARPA has announced the first phase of a shiny new program called RACER, which stands for Robotic Autonomy in Complex Environments with Resiliency. I'm not sure why they couldn't have just left it at RACE, but that's government acronyms for you. Anyway, the RACER program is all about high-speed driving in unstructured environments, which is a problem that has not been addressed by the commercial vehicle autonomy industry, because we have, roads. But where DARPA is going, there are no roads, and the agency wants autonomous vehicles to be able to explore on their own, as well as keep up with vehicles driven by humans. DARPA has announced 3 teams that will each get funding and vehicles: Carnegie Mellon University, NASA JPL, and the University of Washington. And if everything goes well, we'll be seeing some absolutely bonkers off-road autonomous racing over the next 3 years. Rooftop drones for pigeon harassment. Feral pigeons are responsible for over $1 billion of economic losses here in the United States every year. They're especially annoying because the species isn't native to this country. They were brought over from Europe, where they're known as rock doves and are still quite annoying, because you can eat them. But enough of the birds escaped and liked it here that are now stable populations all over the country, being gross. In addition to carrying diseases, some of which can occasionally infect humans, pigeons are prolific and inconvenient poopers, deploying their acidic droppings in places that are exceptionally difficult to clean. Rooftops, as well as ledges and overhangs on building facades, are all full of cozy nooks and crannies, and despite some attempts to brute force the problem by putting metal or plastic spikes on every horizontal surface, there are usually more surfaces, and pigeons, that can be reasonably bespiked. Researchers at EPFL in Switzerland believe that besting an aerial adversary requires an aerial approach, and so they've developed an autonomous system that can identify roof-invading pigeons and then send a drone over to chase them away. Legged robots learn to hike harsh terrain. Robots, like humans, generally use 2 different sensory modalities when interacting with the world. There's exteroceptive perception, or exteroception, which comes from external sensing systems like LiDAR, cameras, and eyeballs. And then there's proprioceptive perception, or proprioception, which is internal sensing, involving things like touch and force sensing. Generally, we humans use both of these sensing modalities at once to move around, with exteroception helping us plan ahead and proprioception kicking in when things get tricky. You use proprioception in the dark, for example, where movement is still totally possible. You just do it slowly and carefully, relying on balance and feeling your way around. For legged robots, exteroception is what enables them to do all the cool stuff, with really good external sensing and the time and compute to do some awesome motion planning. Legged robots are much less comfortable in the dark. However, or really under any circumstances, where the exteroception they need either doesn't come through because the sensor is not functional for whatever reason, or just totally sucks because of robot-unfriendly things like reflective surfaces or thick undergrowth or whatever. That is a problem, because the real world is frustratingly full of robot-unfriendly things. The research that the Robotic System Lab at ETH Zurich has published in Science Robotics showcases a control system that allows a legged robot to evaluate how reliable the exteroceptive information that it's getting is. When the data are good, the robot plans ahead and moves quickly. But when the dataset seems to be incomplete, noisy, or misleading, the controller gracefully degrades to prior perception locomotion instead. This means that the robot keeps moving, maybe more slowly and carefully, but it keeps moving and eventually it'll get to the point where it can rely on exteroceptive sensing again. It's a technique that humans and animals use, and now robots can use it too, combining speed and efficiency with safety and reliability to handle almost any kind of challenging terrain. Scientists develop insect flying robots. A new drive system for flapping wing autonomous robots has been developed by University of Bristol team, using a new method of electromechanical zipping that does away with the need for conventional motors and gears. This new advance, published today in the Journal of Science Robotics, could pave the way for smaller, lighter, and more effective microflying robots for environmental monitoring, search and rescue, and deployment in hazardous environments. Until now, typical microflying robots have used motors, gears, and other complex transmission systems to achieve the up and down motion of the wings. This has added complexity, weight, and undesired dynamic effects. Taking inspiration from bees and other flying insects, researchers from Bristol's Faculty of Engineering, led by Professor of Robotics Jonathan Rossiter, have successfully demonstrated a direct drive artificial muscle system, called the Liquid Amplified Zipping Actuator, LAZA, that achieves wing motion using no rotating parts or gears. The LAZA system greatly simplifies the flapping mechanism, enabling future miniaturization of flapping robots down to the size of insects. RoboBee now able to pivot on a dime. Since becoming the first insect-inspired robot to take flight, Harvard University's famous little robotic bee, dubbed RoboBee, has achieved novel perching, swimming, and sensing capabilities, among others. More recently, RoboBee has hit another milestone: precision control over its heading and lateral movement, making it much more adept at maneuvering. As a result, RoboBee can hover and pivot better in midair, more similarly to its biological inspiration, the bumblebee. The advancement is described in a study published this past December in IEEE Robotics and Automation Letters. The higher level of control over flight will be beneficial in a wide range of scenarios where precision flight is needed. For instance, consider needing to explore sensitive or dangerous areas, a task to which RoboBee could be well suited, or if a large group of flying robots must navigate together in swarms. But achieving precision control with a flapping winged robot has proved challenging, and for good reason. Helicopters, drones, and other fixed-wing vehicles can tilt their wings and blades, and incorporate rudders and tail rotors to change their heading and lateral movement. Flapping robots, on the other hand, must move their wings up and down at different speeds in order to help the robot rotate while upright in midair. This type of rotational movement induces a force called yaw torque. Advances like this will not only help robots in the field with tasks such as pollination and emergency response, but also provide us with more insights into biology as well. Flapping wing robots are exciting because they give us the chance to explore and learn about insect and bird flight mechanisms through imitation, creating a two-way path of discovery towards both robotics and biology, explains one of the designers, noting that the team is interested in studying aggressive aerial maneuvers through the new RoboBee flight model. 2021 sets robot sales record for North America. 2021 set a new record for number of robots sold in North America, with 39,708 units, according to the Association for Advancing Automation. Those sales were valued at $2 billion. Robot sales rose 28% from 2020 to 2021, jumping from 31,044 units in 2020. 58% of those orders came from outside of the automotive industry, a trend that began in 2020 when non-automotive sales surpassed automotive sales for the first time. Traditionally, automotive sales have been the backbone of the robotics industry. More industries recognize that robotics could help reverse productivity declines and fill repetitive jobs human workers don't want. It's no longer a choice whether to deploy robots in automation. It's now an absolute imperative. As we've long believed, and users continue to confirm, robots help companies compete, ultimately creating more jobs to handle their growth. Non-automotive sales saw the biggest growth in metals, which grew 91% from 2020 to 2021, and food and consumer goods, which grew 29% in the same period. With that, we end today's dose of our weekly updates. Join in next time for more of such exciting news happenings from the robotic world.